Hey everyone, let's talk about derivatives. Now, a derivative is the average rate of change or a slope over a particular point. Now, what do derivatives help us do? Well, let's say on this quadratic, we take 2 points. This point over here and this point over here. All right? So if we draw a tangent line for both of these points, all right, we can see that they have different slopes. The derivative of an equation helps us figure this out. All right? So how do we find the derivative of a particular equation? Well, first we can use the power rule for the most basic ones. Power rule. All right. So what does the power rule tell us? Well, for example, if we have a function, for example, a of x is equal to x to the power of n, right? So if we want to take the derivative of this equation, we get a prime of x is equal to our exponent actually becomes our coefficient, so n times x, and we actually subtract our exponent by 1, so n minus 1. Now this over here is the derivative of this equation right over here. All right, so let's do an example. Let's say we have f of x is equal to x squared. All right, so we want to take the derivative of this equation. Now first we have to find n. N over here is equal to 2, so n is equal to 2. Now if we want to take the derivative of this, so f prime of x is equal to, this n becomes our coefficient, so 2x to the power of 2 minus 1, because we subtract our exponent by 1 to find the derivative. Now this all simplifies to f prime of x is equal to 2x. All right. So another rule which we need to consider is the constant rule. The constant rule. All right. What does the constant rule tell us? Well, the constant rule tells us that the derivative d of dx of any constant is always equal to 0. Now, why does the derivative of a constant always equal to 0? So let's take y is equal to 3, for example, over here. All right, we plot this out on a graph right over here. And so we plot this out, and we can see that this constant does not have any slope. And the derivative, it talks about the average rate of change or a slope over a particular point. And if a constant does not have a slope, then its slope is going to be 0. So that is why the constant rule always states that the constant is always equal to 0. All right, so we need to talk about one more rule, and that rule is the constant multiple rule. All right, now what does the constant multiple rule tell us? Well, whenever we have a function, for example, a of x has a coefficient or a constant be multiplied to it. For example, let's take b x to the power of n, all right? Over here, b is our coefficient. B is our coefficient. All right, if you want to take the derivative of this equation, well, that would be a prime of x is equal to, well, we will actually multiply this later after we take the derivative of this, b times the derivative of this equation. So the derivative of this would be n x to the power of n minus 1. And we just smash these two together, and so our final solution is a prime of x is equal to bn x to the power of n minus 1. This is the derivative of this equation using the constant multiple rule. All right, now let's do an example. Let's say that we have f of x is equal to 3x to the power of 4. All right, now we want to take the derivative of this equation. So what do? Well, we first write it as f prime of x is equal to 3 times the derivative of x to the power of 4, all right? Now, what is the derivative of x to the power of x to the power of 4? So dx of x to the power of 4. Well, over here, n is equal to 4. So this 4 becomes our new coefficient, and we subtract 4 by 1, which equals 3. All right. So our derivative of this is going to be equal to, so d of x of x to the power of 4 is equal to 4x. Sorry, that's an n, not an x. X to the power of 3. All right. So referring back to this, we see that we have a constant being multiplied to it. So our final solution is we would multiply this 4 to this 3. So we would get the derivative f prime of x is equal to 12x to the power of 3. That is the constant multiple rule. Alright, so we've talked about the power rule, we've talked about the constant rule, and we've talked about the constant multiple rule. Now we need to talk about the definition of a derivative. Well, a derivative is defined as, with this equation, as the limit of x approaches 0, which we'll talk about limits in a different video, f of x plus h minus x squared over h, alright? Now I'll fix that real quick. Now let's say that we have a function f of x is equal to x squared, alright? We know that the derivative of this is equal to f prime of x, that's f prime of x is equal to 2x. How do we know that derivative of x squared is equal to 2x? Okay, we first have to substitute f of x plus h is equal to x plus h squared, alright? That's how we simplify this weird thing. And so from algebra 2, we know that a plus b squared is equal to a squared plus 2ab plus b squared, alright? So we can use the same rule over here. So x plus h squared is equal to x squared plus 2xh plus h squared. Alright? Now we can substitute this thing right over here. Alright? So the next thing which we get is, as the limit of h approaches 0, we have x squared plus 2xh plus h squared over h. Minus xh. So what do you notice here? We can simplify positive x squared with negative x squared. Alright, so we cancel those out. And now we have the limit of, as h approaches 0, is equal to 2xh plus h squared over h. Sorry, over h. Alright? Now what else can we do? We can factor out an h from the top part, h. We cancel these out, and that just becomes an h. And what else? We can simplify this with one more step. We can cancel this h out, and we can cancel out this h out. So what we're left with is the limit as h approaches 0 is equal to 2x plus h. Alright? With one last step, we can simplify this and get the answer. Well, as you can see, as h approaches 0, h becomes irrelevant, so we cross that out. So the limit as h approaches 0 is equal to 2x. Now, what do you notice about this? This is a derivative of x squared. And if you plug in any other function, we can get the derivative of this using the definition of a derivative.